The global interpreter lock, or the GIL for short, has been an integral part of Python since its introduction in 1997, and at the time was a hero in its own right. In fact, Larry Hastings, one of Python's longest serving contributors, credited the GIL as being one of the main reasons Python became as popular as it did.
I would say that the design decision of the GIL is one of the things that made Python as popular as it is today. So I don't agree with people who say the GIL is terrible, it should never have been added. No, absolutely not. The GIL, part of the reason that Python is successful is because it had the GIL.
However, like all great heroes, the GIL has lived long enough to see itself become the villain, and sits at the centre of many flame wars between Python's biggest supporters and its biggest detractors. It seems even those who work on Python have had enough now, with PEP 703 looking to initiate the process of removing it. But why? What actually makes the GIL so bad? And why is the Python team only dealing with it now? To answer that, we have to go back to the very start and look at what the GIL is, the problems it solved at the time, and how exactly it works. Before we start, I want to make it clear that this will be a very high level overview of everything. I don't want this video to be hugely technical, but I'll be including all my sources in the description below for those that want to read more into it. In short, the GIL is a single mutex lock that protects access to Python objects in order to prevent multiple threads executing bytecode at the same time. These Python objects are all stored in what's called the global state, and every object has a counter denoting how many times it's been referenced. At a time when multi-threaded operations weren't really that much of a thing, the GIL was the perfect solution. It prevented situations where multiple threads could modify reference counts and object states at the same time, which in turn prevented things like memory leaks and crashes, and did it all without the need for any lock management, boosting single-threaded performance. That last part is important as it's the only reason the GIL even still exists. About a year before the release of Python 3.0 in 2008, Python's creator, Guido van Rossum, wrote a blog entry reacting to mounting pressure to remove the GIL, stating,
"I'd welcome a set of patches into Py3k only if the performance for a single-threaded program and for a multi-threaded but IO-bound program does not decrease."
The article also talks about previous attempts to remove the GIL, but states work was abandoned on these endeavours due to the impact on single-threaded performance.
In 1999, Greg Stein, with Mark Hammond, produced a fork of Python that removed the GIL, replacing it with a fine-grained lock on all mutable data structures. However, after benchmarking, it was shown that even on the platform with the fastest locking primitive, which was Windows at the time, it slowed down single-threaded execution nearly twofold, meaning that on two CPUs, you could get just a little more work done without the GIL than on a single CPU with the GIL.
Other projects have been undertaken since, such as Galectomy and PyParallel, but all suffer from similar problems and have all since been abandoned as well. It is worth noting that the Jython and IronPython implementations do not feature the GIL, but come at the cost of a lack of support for CPython extensions. Now we have a bit of background knowledge, why don't we examine how the GIL works in the context of multi-threaded programs? I won't dive too deep into the actual implementation here. If you want to know more about that, I'd recommend looking at the slides for David Beasley's 2009 presentation on the matter, linked below. In Python, you have the main thread and what's called subthreads, which are threads that are spawned from the main thread. At any given time, only one of these threads can acquire the GIL and access the global state. This thread will only release the lock in one of two situations. The first is when the thread needs to wait on any I/O, such as file or a network response. The second is through interpreter intervention, which involves a check performed every 100 ticks. During this check, any pending signals are handled, but only if the main thread is currently active, and the GIL is released and acquired by another thread. This is where the problems start to become apparent. Firstly, ticks are not time-based, instead being loosely mapped to interpreter instructions, meaning long operations can block everything. More pressingly though, threads are not scheduled at all, meaning the next thread to acquire the GIL is simply the first to get a hold on it. This causes huge problems when it comes to signal handling, as the main thread is the only thread that can handle them and has no priority over other threads during the acquisition phase. To tackle this, the interpreter starts thread switching more quickly, which just exacerbates other problems, such as the overheads associated with releasing and reacquiring the GIL, especially present on multi-core systems. These overheads lead to, you guessed it, slower multi-threaded performance, with the effect becoming more pronounced the more cores are involved. It's no wonder then why the GIL has become such an annoyance, and will continue to become more of one as computers become more powerful. But is Python really ditching it? Well, the answer to that is really yes and no. Well, not yet. The plan, if all goes well, is to ditch the GIL entirely by about Python 3.18, But in the meantime, 2 flavors of Python will be provided for each release, starting with version 3.13, one with the GIL and one without. These flavors will thus be focused on single-threaded and multi-threaded performance respectively. If you're building from source yourself, supplying or not supplying the disable GIL flag will determine which flavor you build. Of course, disabling the GIL requires a lot of changes in the core Python implementation, which involve a new reference counting system formed of a combination of techniques: biased reference counting, deferred reference counting, and immortalization, a switch from the pymalloc memory allocator to the thread-safe memalloc allocator, and various changes to the garbage collection system. Anthony Wright's code made a great video covering all these changes in more detail, so I won't rehash it all here. I'd recommend watching that after you finish here if you want to learn more. These extensive core changes will obviously raise some backwards compatibility issues, including the need for all C extensions to be recompiled if they want to run on GIL as Python, and some will need to be modified or either entirely rewritten. Even pure Python code will be affected, as most applications are built with guaranteed automatic thread safety in mind, and may not function correctly once that's taken away. Naturally, major changes like this will take quite some time to be adopted, if they're even adopted at all. While Anaconda has promised to help library developers make this change a reality more quickly, maintainers will likely be hesitant to make any huge changes until there has been widespread adoption. There is also, of course, the chance that this newest attempt to rid Python of the GIL will face insurmountable issues of its own and be abandoned entirely. While I'm hopeful that a GIL as Python will magically solve everyone's problems, I'm hesitant to commit to believing it will. There's still a lot of question marks over how the reduction in single-threaded performance will be addressed, though InfoWorld's video on a prototype of GIL as Python 3.12 shows huge performance gains in multi-threaded applications, which frankly is difficult not to get excited about. From what I've seen, feedback towards this new direction for Python has been mixed, so I'd love to hear what you think in the comments below, and of course if you like the video make sure to leave a like to let me know, and consider subscribing if you want to see more Python content. I'd also like to thank my patrons and members on screen now for their support, and I'll catch you next time for something really cool. See ya!